In this video, I'm going to discuss the math behind exchanging encrypted messages across computer networks. The algorithm I'll introduce is RSA, and then in a future video, I'll discuss some more efficient encryption algorithms that leverage elliptic curves. So the RSA encryption algorithm is based on discrete math, where we can create cyclic groups around a modulus. So we could define the group of all real integers around modulo n as z sub n. Then all operations within these groups will be performed modulo n, like addition and multiplication. We can define a subgroup of all elements in Zn that are coprime with n. Within this subgroup, there must exist a multiplicative inverse modulo n that produces the identity element 1 multiplied with a. And then that would give us a Abelian multiplication group. There's Euler's totient function, which finds the number of integers relatively prime to n, so I'll call that 5n. If n is prime, Euler's totient function is just n minus 1 because a prime number is coprime with everything less than it. Then if n is derived from the product of two primes, p and q, then 5n is equivalent to 5p times 5q. And that would be p minus 1 times q minus 1 because p and q are prime. Euler's theorem is an extension of Fermat's little theorem, which is based on a group's modulus of prime. And so it's an extension because it is more generalized for groups with a non-prime modulus. It states that all integers that are coprime with the modulus will yield the identity element 1 raised to the power 5n. And that produces a sort of like cyclic nature within the group. If you use these elements that are coprime with n, they create these generators that when raised to 5n will eventually regenerate themselves. And so it creates a very cyclic nature, I guess. So if you take some base that is one of these coprime integers with n and raise it to 5n, you get a number congruent to 1 modulo n, the identity element. And then you could extend that and say if I multiply by I one more time, I would get I back. So the extended Euclidean algorithm is used to find a multiplicative inverse of a number around some modulus. And the extension is that it also can produce the bezouts coefficients. That's what would give you your actual multiplicative inverse, which would be the coefficient on either A or B, whichever one you're trying to find the inverse for, because it's producing something congruent to 1 modulo n. Not necessarily 1 modulo n, it's producing something congruent to the greatest common divisor of B and n, but if the greatest common divisor is 1, then it will produce the multiplicative inverse. So suppose you have a fixed exponent for a base that's relatively prime to n, then you can use the extended Euclidean algorithm and exploit Euler's theorem to find the exponent that will give you your base back, essentially producing one cycle in this cyclic group around the generator, which is the base. And so if you had some message and you picked this random exponent e to encrypt it, then you'll get a ciphertext that's whatever m to the e produces around modulus n gives you the ciphertext c. And then using the ciphertext c, which is m to the e, you can raise it to another exponent d to reproduce m mod n if the conditions are such that d is the multiplicative inverse of e mod phi of n using Euler's theorem. So the extended Euclidean algorithm here, I'll just run us through an example. If we were taking 221 and 299, where 299 is your modulus and 221 is the number you're trying to find a not necessarily multiplicative inverse for, but a Bezout coefficient that produces the GCD. In this case, the GCD won't be 1, so it won't be a multiplicative inverse. So the way you start is you take the difference between the modulus and the number you're trying to find a coefficient for, and you do that. The remainder. You would do 299 divided by 221, and the coefficient on 221 is 1 with a remainder of 78. And the idea here is, now that we've found a remainder, we want to find a number that divides into the remainder and also into 221. Because if the number goes into 221 and it goes into 78, then you know it produced a divisor of 299 as well. So you try to do that, and you find that 78 goes into 221 2 times, but still has a remainder of 65. And you repeat the steps. You need to find a number that goes into the remainder, which was 65, and also 78. And we find that there's a coefficient of 1 on 65 when dividing it into 78, but still a remainder of 13. And so then we repeat the steps again to find a number that divides the remainder of 13 and also 65. And 13 does divide 65, which means that 13 is the greatest common divisor we found for 299 and 221. But we still haven't found Bezout's coefficients. So if we backtrack through and continuously rewrite the GCD 13 in terms of the left sides of the equation, then eventually we can work our way back to coefficients on the original two numbers to produce the greatest common divisor. So we have 13 is equal to 78 minus 65. Then we can rewrite 65 as 221 minus 2 times 78 and collect common terms to get 3 times 78 minus 221. And then we can rewrite 78 as 299 minus 221 and get 3 times 299 minus 4 times 221. And there you have Bezout's coefficients for your two numbers to produce the GCD of 13. We can manipulate the extended Euclidean algorithm to first avoid the backtracking step and just find Bezout's coefficients on the first pass of computing the GCD. So we'll have our initial conditions that we know to be true, and we're going to write the numbers a and b, which we're finding the coefficients for, in terms of each other. So we set up the red equation to be fixed in place for the first number and the blue equation for the second number. Then for the first remainder, we can set up the calculation in terms of the red and blue equation with a q multiplied by the blue equation. And in this case, q is 1 because there's no, you just multiply 221 by 1 to produce the remainder when doing the division of 299 by 221. So we get 78 as the difference between the previous two equations, and then we can rearrange for the x and y coefficients corresponding to the remainder of 78. And the equation for the remainders in the update is x0 minus q times x1 for x, and y0 minus q times y1 for y. And then we can update our x0 and x1 for the next step and repeat the operations for the next remainder, which is 221 minus q times 78. And so in the update, your x0 becomes x1 and your y0 becomes y1. And then the new x1 is the equation that we found above, so x0 minus q times x1 and y0 minus q times y1. And we can just cyclically do this computation until we eventually get the coefficients associated with the remainder. That is the GCD of a and b. And that would be 1 if we know them to be coprime. So this means if we pass an encryption key into this function that is coprime to phi of n, we could solve for the d if we know phi of n. Basically, d is your Bezout coefficient on E when doing the extended Euclidean algorithm on E and phi of n. In 1977, RSA was invented and named after the three inventors, Ron Rivest, Adi Shamir, and Leonard Edelman. And their process was as follows. You pick two random large prime numbers, p and q, then define your public key modulus n as p times q. And you'll keep secret phi of n. You'll compute phi of n as p minus 1 times q minus 1 and select an encryption key E such that E is less than phi of n and the GCD between E and phi of n equals 1, which is another way of saying E is coprime to phi of n. Then you'll solve your decryption key D using the extended Euclidean algorithm to find the multiplicative inverse of E mod phi of n. And this is part of your secret key. You don't share this. You share your public key, which is just the pair E and N, the public modulus and the encryption key, so that the other entity knows how to encrypt messages to you. You can send this over as plain text because if it's captured, it only gives information on encryption and doesn't give information on decryption of a ciphertext. Then you can delete PQ and phi of n after the decryption key is computed because they're no longer needed. And then just to note the security of RSA, it's based on the hardness of factorization of large integers into their prime factors. Computing D from the public key that's shared, E and N, is hard because you essentially have to take N and find the two prime factors for it, which is an algorithm that doesn't give security equal to the bit length of your key or your modulus. In fact, much less because there's some relatively efficient algorithms for doing integer factorization. And there are more secure methods of generating public keys that leverage elliptic curves, but I'll go into those in later videos. Okay, so I'm going to implement the RSA encryption algorithm using just a basic client-server application. So I'll run the server on a Raspberry Pi I have, and then the client app will just run on my laptop. I'm just using a simple socket library to create a connection with the fixed port number. And then the first thing I'll do is send over my public key, and then use my decryption key to decrypt all the messages from the server, which will be encrypted using my public key. And I've just fixed in place the two large primes I'm going to use. For the purpose of this video, I'm using 32-bit numbers. So far from secure, but it's just to show how the algorithm works. I'm not trying to have my laptop spend a ton of time decrypting messages. So I've fixed in place the P and Q, the encryption key, and the modulus. So in order to solve for the decryption key, I'm going to need to set up this getKey function. The decryption key I'm going to output from the extended Euclidean algorithm, which is the encryption key and the phi of the modulus passed to the extended Euclidean algorithm. That I explained in the slides to solve for D, and I've given a little block comment above to explain what D is relative to E and phi of n. So D is the multiplicative inverse of E mod phi of n. That means that D times E is congruent to 1 mod phi of n, and that if we use the extended Euclidean algorithm to solve for the Bezout coefficients of D times E plus K times phi of n equals the GCD of E and phi of n, we will get the multiplicative inverse of E in D, because we know that their E and phi of n are coprime, giving us a GCD of 1 on the right-hand side. And then conditionally I'll return, so if the modulus is returned as less than 0, then, if the Bezier coefficient on E, which is your decryption key, is less than 0, I'm going to convert it into a positive integer around the modulus. So it's already negative, so we'll just add y1. Otherwise, just return y1. Now, when we're going to decrypt the message, we're going to have to raise the message to some power, the power being the d, which is returned in y1. So now we need a power mod n method that's basically going to repeatedly multiply a number by itself in order to get back to the original message, basically. So you're getting the ciphertext, which is already raised to the E, raising it to the D, which gives us the plain text back. So the idea here with the Raspberry Pi server is I'm just going to send one character at a time. And so we know that whatever 8-bit number was passed across, the message is going to map back to a character that's only 8 bits. So I'm just going to return the lower 8 bits of the result. And then the decryption function is basically just going to take the message that we get, and I'll send it over as 32 bits. So considering the modulus is 32 bits, we'll take the
share a public key.
So we need to pass both the encryption key and the modulus, which are both 32-bit integers. Gonna pass that as a 64-bit integer called public key. So we'll cast basically both into 64-bit integers and left shift one of them. I'll left shift the encryption key by 32 bits, then or with the modulus. Then we'll send this over the socket descriptor. So basically you send byte buffers across the socket, and here I'll just give the base address of public key, and you can send it over as a bunch of the 64-bit number as a bunch of bytes. So there'll be 8 of the bytes. Do a blocking. Okay, so now when we receive the message back and we decrypt it, I'm gonna say if we decrypt an exclamation point, that means to close the connection. Otherwise, we'll decrypt the message. So read from the socket. And then let's print the character we've read out to console. And once we receive the exclamation point, we'll just close the socket. Okay, now let's implement the server side. Also, do want to quickly just go through some minor assumptions about this. Only sending one character at a time obviously is like a huge oversimplification of how RSA would be used in practice. These numbers would be significantly bigger, like the search space it takes to search a 32-bit integer, and just brute force search for a decryption key that works is not really difficult for most people's laptops, but these would probably be like over 1,000 bits long. Then the one thing with the math that comes to mind as an assumption you should lay out is one, your encryption key, or sorry, your message base. So the actual plain text you're sending, the plain text character, it has to be co-prime with the modulus, or relatively prime to the modulus. Otherwise, you're sending a message that doesn't follow the cyclic nature 1 raised to 5n. It's the subgroup that's co-prime to n that has that cyclic nature. Now, the odds of that character being not relatively prime to n means it's a multiple of either prime 1 or prime 2, which is basically the odds of that happening is 1 over prime 1 plus 1 over prime 2. Here we just need an encryption function, which is going to use the power mod n because you're just raising plain text to the public encryption key. So whatever public encryption key you found, you pass in as a power, and then here returning a 32-bit integer because there's really no saying that an 8-bit character will stay 8 bits when raised to a power modulus of 32. All right, we'll be returning result as the 32 bits. The rest of it is the same. Yeah. Then the encrypted message. So I'm going to put the encrypted 4 bytes in that, pass back the byte buffer as just the pointer to this global. Eight-bit chunks of the encrypted jar to pass it over the buffer as a byte buffer, over the network socket as a byte buffer. So it's the lowest. Yeah, passing it over little endian style. All right, so now we're going to receive the 8 bytes we send across right away from the client. We'll receive the modulus in the lower 4 bytes. So cast this to a 32-bit number. 32-bit unsigned 32-bit integer, and then the encryption key comes in as the upper 4 bytes, so it's pointer to buffer 4 bytes in. So I'll type on standard in what character I want to send off. Put it in the user input char pointer to the encrypted message that we will send using the encrypt function, which returns the message from. So this is going to be the char pointer that we're taking in from standard in that we're encrypting. So pass the address. Key, the modulus. And then send it out. All right, I made a mistake. The Y1 computed in the last cycle here is not for the GCD, it's not for a remainder 1, it's the following with a remainder 0. And so and the quotient would have been whatever 1 went into the next lowest, then whatever the E was. Okay, so this should be wide 0. Just send it. That looks right. Start sending messages over. And there you can see we're decrypting the scrambled integer back into an 8-bit character and sending across the message hello, with the only person with the secret decryption key being the client to decrypt the message. See if we get the close connection. There you go. Yep. So thank you for watching.